acceleration here is going to be 3, and the mass is 2 plus 6, which would be 8. So this would be 24. 24 m, right? Because we don't really know what the m means, right? Now on the bottom here, case B, we have they're asking about which. Oh, so about that point. So let's look at point B now. Wait, we figure out this is 24. Point B is also being pulled this way, right? But only this mass will matter then, because the mass is ahead of the points being pulled, right? And therefore it would be 6 times and 8, which would be 3, so it would be 18. So over here we have 18. Are you guys following? Yes, you're right. It depends. Let's think about it. Very good question. Give her English. All right. So if the force is acting here,
it's the right one.
If the force is acting here, I have to count both of these, right? Or if the force is pulling it here, and like a tether, and it's pulling both of them, and there's of course a tether connecting these two. Let me just show an example. And if I'm asking about the force here, of course both masses matter, right? Because I'm pulling both masses. Think of it as if it's you pulling it. Are you working on what? What are you working on? You're moving this cargo. What would I be moving if I'm pulling it here? Am I moving those two? So if I am in a tug-of-war competition and I go right there, right? My force is applied on this thing. So when I'm in tug-of-war, I'm actually pulling on the people behind me? No. That makes no sense. Are you with me, I'm saying? So it has to be only the stuff that's ahead of me.
How did you get to 24?
Because I'm not pulling what's behind me. I'm only pulling what's ahead of me. Right? So this thing is pulling this way. And if F equals MA, M is 2 plus 6. I'm pulling all of that. So it's 8 and M is 3. A is 3. Alright? Now let's talk about C. It's 3 again. But what is C? C, this time, it's pulling. Or what is it pulling now? Just a 4. Right? So it'd be 12.
Okay.
Right? What about D? D is pulling these two guys. Right? Because this time we're starting this way, right? So that'd be
15.
5, which is be 15. So if you rank them, it would be from rank them after attention or compression. Yes, so it would be A, D, the A, B, D, C. And then you have to justify it. So if you have to explain the whole thing, you would say the force only acts on objects. When it's pulling, it only pulls things that's behind it, right? When it's pushing it, it only pushes things that's ahead of it, right? So by that logic, we just follow along the whole thing. Make sure you do that. Guys, you have to practice. By the way, this is one thing that's good about practicing antipress. You have to practice writing out the whole thing, all right? That's why the FRQs are for. Now, blocks on the inclines.
Mr. Lima,
Yes?
for example, question like that, if when I ask for explain, would you show our work? Would it count for points?
Yes, but not without words. You have to actually explain what. So I would say something like, as seen in the work above, right? Well, the force is only acting on objects that are either ahead or behind of it, depending on the situation. So if you're accelerating to the right, only the objects to the left of it are being pulled by it. So you're not going to count the objects to the right of it because I'm going towards there. So it doesn't make sense for me to be pulling that object if I'm heading towards it, right? So it's only the objects to the left of it that would count in that case, right? If I'm accelerating to the left, though, it's only objects to the right of that are being pulled. Because I'm heading towards the left, it doesn't make sense for me to be pulling the object to the right. Are you following what I'm trying to say? However, you could talk in here in terms of the compression that's being made. But that's a different story. All right? All right. We did it this way. Okay, the box for the inclined plane, force acting on it. So we have the normal force. Notice how they did not split the weights here, right? And they have a force on the inclined box and the tension that's on the rope. Now, the force of the incline is like the friction that's being exerted. Now, notice that they chose to put the force that way. What would happen if when you do the math and you solve it, you get a negative number for that force? It means that your diagram was wrong to begin with, and that force was actually supposed to be going that way. Are you with me? There's actually no wrong answer. You could get that, but it depends. If this thing is tending to fall or tending to go up. It depends on whether the weight or the tension is the most. Are you with me? Yes?
Oh, yeah.
Now, if this is tethered to a rope, let's read it to make sure we understand. So I have heavy boxes sitting on rest on the incline, and there's friction between the box and the incline. The rope is pulling the box in the upward direction to the left, parallel to the incline. The physical student has drawn a 3-bar diagram. Alright, so this thing is moving to the left. Alright? This thing is moving to the left because of the force, so there's a movement. We don't know if it's changing or not. We don't know anything about that. But it's the 3-bar diagram. So then what, if anything, is wrong with the student's 3-bar diagram? If something is wrong, explain the error and how to correct it. If the 3-bar diagram is correct, explain why. Now, you have to practice phrasing the whole thing. Phrasing exactly what's wrong, exactly what's right. That's what they would expect from you in a test. That's what they expect from the FRQ. They want you to explain the whole thing. So, let's go step by step and you guys help me out. Gabriella, is the normal force drawn correctly on the diagram?
Yeah.
I agree. Catherine, is the weight drawn correctly on the diagram?
Yes,
Sure. You could have split it, right? Or but that's fine the way it is, right? Legals, guys. If you get it right, the men the legal. Right? So, Laura, can you make sure you feed people? Alright? Alright. Laura, what do you think about the tension? Is it drawn correctly on the diagram? Yes. Alright. Chris, what do you feel about the force on the incline on the box, which is probably friction?
I think it's wrong.
Why do you think it's wrong?
Supposed to go the other way, 15 towards left.
Right, so the friction should oppose the direction of motion, right? Okay, but do you see, how would we also, now, Melissa, attempt to put this all in one big sentence. All right, go ahead.
Saying everything that's right is wrong.
Right,
Okay.
you're answering the question.
Okay, the normal force is accurate because it's perpendicular to the.
See, she's saying why it's accurate, very good.
And then the weight is also correct.
Because it's supposed to be vertical.
Yeah.
Yep. Okay.
It's in Y components. And then the tension is correct because that's the way the rope is.
Being pulled towards.
Yeah,
Uh-huh.
pulled. And then the tension is incorrect because.
Not the tension, the friction.
The friction, sorry. The friction is incorrect because it's supposed to oppose the way that the tension is going.
Right, or the direction of motion. Right. So, what?
Can you just say everything else is right but the friction, and then explain why the friction is wrong?
Or would you not get
If something is wrong, explain the error and how to correct it. So in this case, they actually only wanted to say what's wrong and how to correct it. But you got to be careful because I want us to practice telling you everything because sometimes they will say what is correct what the student's thinking. So it's better to just practice justifying everything, right? But technically, what the question is actually asking is to say identify the mistake and correct it. And if everything's correct, then explain why. Now, it's actually better, and I told you this, any question like this, always focus on what's right, what's wrong, and whether or not it's correct in general. Right? So you have to justify everything is right. Now, if it's an actual AP test, you answer just the question, which would be just this. The student's diagram is incorrect because the placement of the friction arrow is in the wrong direction, given that friction should oppose the direction of motion. Right? The friction should not be helping the box go uphill. It should be, right, slowing the box down, right, for going uphill. It should be making it more difficult for the person to do the job. All right, let's keep going like that. Yes.
You see that the friction has to be pointing the other way because the box is moving.
Because it's moving that way. It just makes sense, right? I mean, if the box was falling down the hill, it should be going up. Now, actually, that's actually a very good point. Another good get legal. Because if you ask me, if you make me think of a good thing to talk about, I'll give you labels as well. Now, let's say the weight was bigger. Forget this is not in there, okay? The weight was bigger than the friction. What would happen now? The tension.
all of them?
It's like the guy trying to go uphill, but he can't, right? He's failing. Which way direction should it go now with friction? It would be correct.
Yeah.
It would be correct. Because friction is trying to help the guy not lose the box. So friction doesn't have a direction. It opposes the direction the thing is trying to go at. Are you with me? Very good question. Alright. Let's do this one. Free bar diagram. Draw it quickly. Let's do this. And Derek, do it on the board. Hurry up. Let's go. This is supposed to be an easy question. Huh?
Yeah, what is that?
No, it's just like, it's supposed to be like representing like a,
Like the air, the wind. Oh.
so it tells you which way it's going.
You want like
Derek, go ahead real quick.
Yeah. They have to be accurate, but the magnitude has to be accurate, okay?
the magnitude?
Yes, the magnitude of them have to be accurate. There is friction. You guys do it at the same time. Don't just wait for Derek to do his, do yours. Sure, next time. We don't need this one right now.
I think that's wrong.
Okay, gravity is an acceleration, not a force.
This would be
Okay? What you mean is way y and way x. You don't have to split them, but if you don't split them, you just need one. Are you with me? So you could have put just like one going down. But if you're going to split it, then you want to put weight x or weight y, right? And then weight x. Now, this is very important. If you're ranking them, ranking the forces. This is actually very important. There's a way to do it. Okay, that was the first thing. You get one Lego, right?
Can I rank them and get two?
Wait, is this?
Alright, sure. Now let's try to rank the forces and explain why. Which arrow, okay, should be the biggest on our rank? WX? That's already wrong.
Isn't weight y supposed to be down?
Alright, yes.
What are the bottoms?
What?
What's the bottom ones?
WX
Wait,
and WY.
WX and WY. Now, why did I say it's wrong? What's the angle? So how do you split the weight then? It's they're equal. It's the point at which weight x and weight y are the same. Because it's a square, isn't it? So each, if you think about it, the sine and cosine here will be the same. Right? Which means the components of weight x and weight y have to be tied.
And the normal force has to be tied, right?
Yes, because they're equals weight y. I got labor for that. Right? Then, what about friction? Friction will go last, yes? Because it's losing this battle, clearly. Right? Does that make sense to you guys? Because otherwise it would be going flying to the sky or going through the thing. If it wasn't equal, it would be moving in that direction, right?
No, but the normal force is also equal to the y component. Because it's equal to the x component, then they're all equal.
Oh, yeah, you're right. So it has to be equal to that because that equals to that and that has to be equal to that. Right? That's what you're saying. Very good.
I thought that weight y was supposed to point down, not like that.
No, it points perpendicular to the surface.
Because it's divided. Because it's separated.
Perpendicular to the surface. Weight y. If you're just doing weight, it goes straight down.
Yeah, that's why I was asking.
Just weight is straight down. Weight y is perpendicular to the surface. The one that normal force is opposing. Okay? Guys, I like to split them because it helps me do the equations. Yes?
Shouldn't weight x be the same as friction?
No.
It's opposite and equal force.
It's falling. It's accelerating down the ramp.
I don't get why
If they were
it's
equal, it wouldn't be equal.
Speeding up as it slides down.
accelerating. I don't get why.
Alright, he knows it's wrong. Okay. So, free body diagrams. So we did two separate free body diagrams on the objects. Alright? And he has the labels and what the forces mean. There is at least one thing wrong. Let's just do what it says to do. Don't explain everything. Identify all error or errors and explain how to correct them. Alright, let's do this, guys. This is object A, the bottom one. This is object B, the top one. There is friction between the boxes and between the tables. It's similar to something that we did together, so it should be really good. Don't say it out loud, just work on it. He has the labels, so figure it out.
What's wrong?
Yeah, what's wrong?
Oh, it's two on air. Okay.
Something is wrong. I can see one thing is wrong already.
Alright. A is accelerating.
Because it also has to include B, doesn't it? For the normal force.
Well, it doesn't say that K is not equal to A plus B's weight. Normal force on A by B. He has that point pointing down. Yeah, and he has the weight of A on the Earth, which is L, which kind of makes sense. So when you do the equation, you're going to see that K equals P plus L. So he's not saying that K does not include the weight of block B. It kind of does, actually, because by putting these two, it shows that there's a force acting down on it, right, which is the P, plus the force that Earth acts on A. Right? That's not what's wrong. Huh?
The arrow thing is a rope?
It's a force, yeah.
No, but is it a rope pulling on it?
Sure. It doesn't matter. It's a force. It says...
It says tension, that's what I'm asking.
Yeah, tension.
Okay.
Okay, so it is a rope.
Okay. And it,
I don't think anything is wrong with object A,
the magnitude of
except for one little thing.
the magnitude, right?
So
There's one thing wrong with object A. Object B is fine.
But I thought P was supposed to point up.
What?
Because then you just say that P and L, right? I thought it was supposed to point up.
What? Now, P is a normal force of A on B.
Exactly, so
Isn't
she's
that
going to
the
be
weight
up.
of-
'cause
It's
A
basically
is
the weight of B on A. You can call it that if you want. It's the contact force between B and A. There's nothing wrong with that.
wait,
Yes.
not the magnitude.
The magnitude being wrong, yeah, the magnitude being
Because
wrong.
the friction is larger than the force is actually traveling in.
Not to scale.
Oh, then nothing.
So we're not grading the
I don't
magnitude.
think there's anything wrong.
Yeah, then nothing wrong.
There is something wrong with it.
It is?
It's breaking the third law.
the opposite.
Oh, because there should be
Oh,
another
there's no
force.
pair.
Another no.
Something is not paired. All right, so this is paired with the Earth. We're not showing the Earth in the diagram. That's why it's not there. Okay? That is thing, which means there's C is paired with, P is paired with C. Because C is the normal force of B on A, and P is the normal force of A on B. So P pairs with C. So let's check the laws, right? So P and C are paired. This is paired with the Earth. That's paired with the Earth, right? That's a force that's paired by whoever's pulling the rope, right? It's not in the diagram, but whoever's pulling the rope is also suffering that force back, right? So it's paired to, that's friction. We're not diagramming the surface, so that's why it's not showing that, but it's, you know it's paired there, right? This is the problem. That is a friction acting on object B, which is being acted by a friction between A and B. Where's that friction here?
Oh.
You can think of it as, what's pulling B forward? The friction between B and A.
Well, there is friction.
But that friction must therefore be doing what to B, to A? That's right. There's supposed to be another force here equivalent to E. Call it whatever you want, Z, whatever. Which is the friction between B and A. Otherwise, that's not paired. Everything I'm trying to say? Third law? So, I actually did this in the video. By the way, if you have not watched that video that I recorded when I read the crazy problem, make sure you do so. It's a 30-minute long video where I break down that problem in the quiz in a little more detail. All right.
Wait, what was wrong with
Keep going.
Wait, where's the video?
It's on Science Classes Great. All these videos are on Science Classes Great. So if you ever miss class or just want to review something that we did, you can always do that. All right, let's keep going. They put it back this time. You see? Now they put the force. And they're kind of asking you to rank them from greatest to smallest. Right? I'm going to skip this for now because I want to do some other stuff. No collision stuff right now. Ooh, love it. That's the whole, we already talked about this. All right, when the contact force is bigger, right? It depends on, okay, so think about it. What's this contact force right there? Something related to 5M, right? What about down here?
6M.
6M, and now here? 9M, right? Now, the contact force that you're pointing to here is A, so what's that? 6 MA. Well, there's no A, so it just be 6 times. Well, normal force equals the A. So mg, yeah. This would be 6 mg, right? And here, 3 mg.
Why
Are we
MG?
skipping?
Because this acceleration, without the g, is not a force. It's just a mass,
B is 5.
right? We're talking about the weight, right?
You might skip B.
Oh,
It's 5 mg.
B is 5 mg.
D is
This is mg. This is mg. And then this one, 4 mg. And then that one, 3 mg. And what about here? That's the one that wins. How much is that?
0.
That's OMG. Sorry, I just couldn't resist the joke there. Alright, anyways. Do you understand why?
Wait, don't move it. Don't move it.
You broke everything. You went to war.
Oh, you get why? So then if you were ranking them, it would be A, B, F, G, and C, and then E, and D. Do you understand why though? That's easy, right? The normal force equates to all the weight that's sitting on top of it, which is the whole thing about how you drop the hammer thing, right? Why do you drop the hammer? They say to drop the hammer how? To handle down? Why? Because when it hits, the weight at the top will add more mass. Exactly. Only because the head of the hammer is heavier, right? Okay. The weight of the rock, the rock with the weight of 10N is resting at the table. The student makes a number of statements about the situation. The first statement today says, the weight of the rock is a force of 10N by gravity in a downward direction. Is that right? The weight of the rock is a force of 10N by gravity in a downward direction. Nothing wrong with that, right? Fine. That's correct, because the weight of the object is mg, right? And they'll give you the weight of 10N. It's going to be 10N. If it's resting on the table, its weight, its real weight, is still 10N, right? The reaction force to this weight is a force of 10N exerted on the rock by the table in the upward direction. Is that correct? Yes, by the Newton's third law, right? For every action equal to opposite reaction. The normal force exerted on the rock by the table. The normal force exerted on the rock by the table is a force of 10N. The reaction force to this normal force is a force of 10N exerted on the rock by gravity in the downward direction. Okay, so now what he's saying now, there's a weight of the object. That's 10N. And he's saying there's a reaction force that happens to that weight on the table. That's 10N. Now he's saying a reaction force to that reaction force is the reaction force that's gravity.
Wait, what?
So is the normal force a reaction force to gravity? And you then say that gravity is a reaction force to the normal force, is what you're trying to say. That's what this is saying. The normal force exerted on the rock by the table is a force of 10N. The reaction force to this normal force is the gravity.
Okay, right? Yeah. I mean, it doesn't really
So it's the weight.
conceptually make sense.
I like where she's going with it. It doesn't make sense to think of the gravity as a reaction to the normal force.
But it's just, yeah.
Because gravity, it's actually, it doesn't make sense. There's a reason there. The weight, there's a reaction to that force. What is it? The weight of the object? Is there a reaction to that force? Yes, the earth is being pulled back up. That's the reaction to the weight. So you can think of, does the weight have a pair that reacts to it? Yes. So the normal force, in that case, but then for every action, so if you think about it from the angle of the normal force pushing the arc up, you can think of its reaction to be that thing. But that's like calling the reaction the action. And that's what she's saying conceptually doesn't make sense. Right? That's why I think it's wrong with this statement. It's that the normal force is not causing the gravity. All right? But in a way, they are paired. Just the same. All right? If the 10 Newton rock is lifted off the table by a hand, that exerts a 12 Newton force upward on the rock, the reaction force of this total force is a 10-Newton force exerted on the hand by the rock in another direction. So now I pick this up with a 12-Newton force, right? Are you with me? So that means the 10 Newton down, that the weight is still there, is the reaction to the 12 Newton up that I'm doing.
No. It's got to be 12 newtons down, because otherwise you're creating.
Okay, but for every action, there's an equal and opposite reaction. So I'm putting 12 Newtons of force on this object. Where's the reaction?
Wait. Isn't it weight?
This always stops. It was easy to now, right? Okay, so I pick up a rock or pick up this thing, and I exert 12 Newtons of force on it. Where's the reaction?
Drag.
Isn't it the weight?
Is it drag?
Weight and drag.
The weight is not the reaction because
Oh, wait, gravity can't be.
the weight is still there.
Yeah. So then,
Now, is the weight actually acting on 10 Newtons in my hand? Is the weight acting on my hand?
okay, then normal force down.
No, it's not.
No.
The weight is the earth acting on the object. Is there now 10 Newtons acting on my hand? Yes.
Normal force.
But is that the weight?
Normal force.
Now?
I'm so confused.
Right? Confused. Guys, think about it. I'm pulling 12 Newtons up. Is something pulling me 12 Newtons down?
Is it normal force?
There's got to be.
There's got to be.
It's not drag. It would be the same thing in a vacuum.
How do I pull it? How do I pull it? How do I touch it though? How do I grab this?
Contact.
Friction.
Got it? Sure.
Really?
Of course. Static friction.
Oh my god.
Okay.
So it's correct.
Alright?
Mind blown.
Mind blown.
So that one's correct.
So it's correct based on static.
Good job. Good job now. Alright. We solved the problems. Alright. I love these weight problems, okay, that we have here. By the way, there are so many more A-tippers that we have time to do. Like literally much more. What page are we in? 168? I remember that. So it goes all the way to 108. It skips around though. Is that what the problem is?
Big time, because we're already on like.
No, 9, and that's 7. It's skipping one index page for some reason. I have to rescan it.
Do I get labels for building of labels?
Anyways, there are 40 pages missing. So we're not, it's 40, no, we're not going to be able to finish in the 10 minutes because next class I want to do lab, so I'm not going to be able to finish it. Well, actually, the next class will start with the dynamic step by cube, but that's a different story. All right, so, okay, so,
Next class.
next class.
Okay.
Okay, so if this thing is accelerating upwards, now let's think about it. If it's accelerating upwards, a force is acting on the elevator. Not on me, but I am on the elevator, and therefore, as the elevator moves upwards, right, that it will increase the contact force, right, between the scale and the table, and now also by the same token between me and the scale. So it will make the normal force go up. Does that make sense to you guys? Meanwhile, in a situation like this, when it accelerates downwards, it will decrease the contact force because it's acting on the elevator, not on me. So what I want to keep doing, what I was doing, which is staying where I am, right? So that means the elevator will drop below behind me, which will lower the contact force for at least for a little while until I start accelerating as well. Is that clear for everybody? So in this situation, the scale reading will go up or go down. Remember, the weight is the apparent weight, is what the scale is measuring. Right? The scale is measuring the apparent weight, which is the normal force that's acting on the thing. The scale is not measuring my weight; it's measuring the normal force. Right? So, is this going to increase the normal force or decrease the normal force? Increase it. So the scale reading should go up, and in here the scale reading should go
Down.
That would be a cool lab to do. You can do it on the elevator. All right. Now, what about here? I am moving downwards down. Oh, we forgot to look at that. Let me give you a second. I was moving up. That changes everything. We were moving up, and then accelerated up even more. Now it's different. I forgot about that. We have to look at the velocity, see what it's doing. We are moving up, and now accelerated up even more. Yeah, it should increase or decrease? Now I'm moving up, and it starts going down. I keep going, so it decreases, right? Now in this scenario here, I am moving down, and it accelerates upwards. That's when the elevator starts slowing down. You can feel it. It feels what? Heavier. And then about this situation, I'm going down, and it accelerates down. Lighter. Does that make sense to you guys? All right, let's keep going. Let's see if we skip pages. 117, 119. All the interpreters are missing pages. This whole time, we're only seeing a sample of them. All right, it's fine. I have to rescan it. That makes me very sad. No, I have them all split. Oh my gosh, we only have the odd pages. The entire thing.
Do you forget to scan the other side?
That's odd.
Yeah. Maybe you forgot to scan the other side.
Ah, great. Okay. No, it's fine. I mean, we don't have to. Even doing half of them, we didn't have enough time to do them all, anyways. So, but that means you can do the odd pages for more practice. The even ones, yeah. All right, let's go. This. The block is tethered to a frictionless ramp, right? And the block is at rest. Is the normal, we already did this, but let me just think about it. Is the normal force exerted on the block by the ramp greater than, less than, or equal to the weight of the block? Think about it. I talked about this. When you're like this, part of the weight is going where? To the table, and part of it is going down. What is the normal force? The opposition to the weight that is? That is a fast, so it could be less than. Is that clear? All right. So which one has a smaller normal force? This, okay. Since both blocks are identical, I think the normal forces are the same because in each case the normal force will be equal to the weight.
No.
No, it's actually, this one is not equal to the weight.
Yeah.
That's equal to the fraction of the weight
In the y direction.
that acts perpendicular to the surface. Right?
So wouldn't the first one be smaller?
First one will be bigger. Because this one, part of the weight goes down, part of the weight goes to the surface. Right? Yes? You got it? Alright. Again, by the same token, normal force. Bigger or smaller? Now, without that force, what does that do to the normal force? Think about it. Part of it pulls it forward, part of it pulls it up. What does that do to the contact here? Isn't it pulling a little bit up?
Yeah.
Now, it's not enough to make it go up, because the weight is probably bigger than that, and it is. Are you with me? But it's still diminishing what? The contact, which actually lowers the friction, makes it easier to pull forward. Well, I told you about this, right? If you lift the table and then pull it, it's easier, right? So, let's see who's right. The normal force is 50 newtons. Since there's a weight of the box, the normal force makes a Newton's third law pair with the weight. Is that true? It does not make a Newton's third law pair with the weight. If you do a free body diagram of this, you will see that the force, there is a weight going down, right? There's a normal force going up. There is a force Y that comes from this going up. And there's a force X that comes from this going up. And then there's a friction going this way, right? If there's a friction, right? But my point is, the weight, normal force is not equal to the weight in this case. If you do the dynamics equation, you would do N plus Fy equals weight. Therefore, N equals weight minus Fy. That fraction that pulls up lowers the normal force.
Isn't there tension also?
Yeah, well, it's this one.
The force.
Right, the force points to the weight. Now, so he's wrong. He's wrong because the normal force isn't always paired with the weight. Right? It could be another force in that direction. Correct? But in this case, there's also an upward force of 40 newtons on the box. Is that right? No, it's wrong.
No, it's blue.
It's not a 40 newton force off the box.
It's blue.
He was almost right. Right? Because the force upwards is not 40. It's a fraction of 40. It was so close. Right? 40 times the sine of 30. Right? Actually, sure. Actually, only a part of the 40 newton force is acting upward. What we have to do is trigonometry to figure out how much. And then subtract this from the weight to get the normal force. Aha! Smart Chloe. She's kind of right. Don't say we can't figure out the normal force until we know the acceleration. The greater the acceleration, the less the normal force will be.
Acceleration doesn't change anything about
That's going in the x direction. He actually, this part is right. The greater the acceleration, the less the normal force will be, because but because the more I pull this way, the more I'm accelerating, the less I leave left to fight the normal force. But if I'm told it's 30 newtons, right, then that's going to help determine what the acceleration is, period. All that matters now is the friction. You know what I'm saying? So that doesn't make sense. So this is a very good one, though, to practice things. All right. Now we're getting to the fun stuff.
Yeah.
I think I might still have to take half the class next time to do more of these, because that's where it starts getting harder. All right. A system of 2 blocks is connected by a massless string, so it's an ideal spring. Okay, so check this out. Rank the situation based on the tension at spring at point P. So they give you the 2 masses, and they're asking you, how does that affect the tension at that point? Now, if this thing is accelerating left, what do we learn about this? What is the only thing that matters? The mass that's what? Pulling on it. Is that true? In this case? Think about it. If I'm pulling that mass, right? So it's only the mass that's being pulled. Correct? Does that mass going to matter for that? Not really. All right? So then, what situation here creates the biggest pull?
Not E.
Notice the acceleration is changing too.
Oh, I see that.
Yeah, because it's 3 times 15, right?
Yeah.
And then these two will be tied,
Wait,
right?
Wait, F. Wait,
And then
wait, D.
we'll tie with this one as well, because it will also be 30, right? And then those two will be tied for last place, right? Now, you could actually do equations to figure this out, but look at it. Think about this object and the tension that's acting right there. That tension T, right? All that's pulling that object is T, right? T equals ma, where m is the mass of that object times the acceleration. So it tells you that all that matters is ma. Are you with me? There is another way of looking at it, though. You can also look at the tension this way, because it's the same thing, right? Isn't it?
Yeah.
But if you look at that tension, right, now it gets more complicated, because that tension is a little different, right? So look at that. Tension equals m, but this one has a force here, a weight. And this one, the weight is not fighting that tension, right? Because there's a normal force that's fighting the weight. It's not even in the same direction. Are you with me what I'm trying to say? Right? But in this case, the weight is in the direction of the tension, and they're going to be matter to each other. So the dynamics equation for this guy will be weight pulling it to the left minus the tension equals that mass 1 times the A. Right? Which means the tension of that object equals the weight, right? The fraction of the weight that's acting in that direction, which will be to the side of the angle. So it will basically be m1 g times sine of theta plus m1a. But since I don't know the angle and all that stuff, is it a smart way to go about figuring out that way? No, because I'm not given the angle. Are you with me? In other words, I could look at object 1 to figure out the tension. And it will be the same, because the tensions have to be the same. Are you with me? But I don't know this angle here, right? And so, did you understand where I got this equation from, guys? Yes or not? If not, let me show you. Weight minus tension. I'm looking at the direction here, right? Why did I call weight positive? Because it's accelerating this way, and I'm calling this the positive direction of the problem. All right, the direction it's going. All right, minus the tension equals the mass times the acceleration. I'm doing an equation for this object, right? However, that weight is just a fraction of the weight that's pulling it down the inclined plane, which remember is times the sine of the angle, right? Not cosine, sine of the angle, right? So that means that the tension, if I send it to the other side, it has to. Whoops, I actually did a math mistake here. It's minus. All right? Because if I send the t to the other side and then this to this side, it becomes like that, right? So actually, it's like this: g sine of theta minus a. But see, the problem is that how do I rank the tensions this way if I don't know this angle? Well, I could, because they all have the same angle. Are you with me? So in that sense, I could look at it that way too, because they will. So let's see if it works. Gravity will be the same in every case. Sign will be the same in every case, right? So still all will matter will be that. So what was the ranking we decided last time? Help me out. What did we decide last time?
E is greater than C equals D equals
E
F.
is greater than C equals D equals
Greater
F,
than A
which is greater than A
equals B.
equals B. So let's think about if you're looking from the point of view of the first object, right? These numbers will always be the same between both objects, whatever the number is, right? And then you have to subtract A out of that and then multiply by A. So in a way you can still do it because you could do 18 times 3, right? Or 15, E was the first place, 15 times 3 is 45. But the problem is that without knowing how big this number is, because we don't know the angle, it's a bad way to do it. But if you did have the numbers, it would all work out and it will have the same thing. Are you with me? So my rule of looking at what's being pulled makes more sense. Are you with me? But I just wanted to point out that by the third law, that tension and this tension are what? The same. So you can also think in terms of what's being compressed, is all I was trying to say. But pick with a simpler, is what I'm trying to say. When you have a problem like this, always look at what is simpler. All right? So the next one. Ooh, I love these. I love these. So the weight gets up here. Free body diagram for this point right here. From that point right there. We have the weight going down, which is the weight of the mirror. Who gets more of the weight here? Instinctively. Let's think about it. What happens with this? The weight gets split. Are you with me? They're not evenly. Instinctively, do you think they split the weight the same way? So how do we figure it out? You got to do vector splits. Now think about it. You go this way, and you go that way, right? Now let me think about this. Is this dot right there moving left or right? So what does that mean about these components? They have to be equal. Otherwise, the dot would be what? Moving left or right. Are you with me? So whatever is the tension, I'll call this tension, this side B and this side A. Whatever the tension BX is, the tension AX has to be the same. Does that make sense for you guys? All right? What about the TY? By the way, they cancel each other out. TAY plus TBY have to be equal to the weight. Are we clear with me on that? Because there's two arrows pointing upwards here for those two things, and they find a weight. Now, let's just look at the first guy over here. Forget all that, let's look at the first guy. Let's think about the two vectors that they have in this angle right here. TAY is this line right here. So TAY equals, we're trying to solve for TA total. That's the hypotenuse, isn't it? You see the hypotenuse of the triangle right there? So hypotenuse, opposite over adjacent. So opposite over, sine of the angle equals opposite over hypotenuse, or TAY over TA, right? So if I'm solving for TA, it will be TA equals TAY over sine of theta, right? The same equation will happen for the other one. TB will give TBY over sine of theta. Okay? Now we know they split the weight. Both of them do, right? So the weight is split between both of them, right? But if you look at this, the angle here matters. Now, does sine get bigger or smaller as the angle gets bigger? As the angle gets bigger, does sine increase or decrease? Think about the unit circle. Increases. So, as the angle gets bigger, this number is getting bigger. What's happening to that number? It becomes smaller. Are you with me, I'm trying to say? So which one has more tension? By that token. They have to have the same x. So the difference is going to be in this TBY, right? But I'm trying to show you that when the angle is bigger, right, which one is going to get more force, have to support? That one, right? Because the sine is smaller, which will make the number bigger. Does that make sense to you guys? Right? Yes? Okay. Very hard conceptual question. Let's see if we have one. I don't think we have time for one more.
No, 29.
All right. So we'll pick it up from here next time and do more dynamics problems.